Welcome student. With this video lecture we are going to discuss the Laplace transform using the unit step function. In engineering applications we frequently encounter the functions whose values changes abruptly at specified values of time t. In electrical circuit the switching process can be described mathematically by the function called the unit step function, which is also known as Heaviside unit step function, which is named after the mathematician Oliver Heaviside. First, we shall define the unit step function. The unit step function or a Heaviside function is denoted by u of t or h of t, and it is given by 0 for t less than 0, and it has a value 1 for t greater than or equal to 0. This is what the graph of the unit step function, which takes the value 1 for t greater than 0 and it has a value 0 for t less than 0. Further, the Laplace of unit step function is equal to 1 by s, as u of t has a value 1 for t greater than or equal to 0. So by the definition of Laplace transform, Laplace of 1 is 1 by s. That's why Laplace of u of t is equal to 1 by s. And Laplace inverse of 1 by s is equal to u of t. So this is what the inverse Laplace transform in terms of unit step function. Actually, the Laplace inverse of 1 by s is 1 previously, but in terms of unit step function we can write 1 as u of t. Next is the displaced unit step function. It is defined as u of t minus a is equal to 0 for all the t less than a, and it has a value 1 for t greater than or equal to a. And this is what the graph of the displaced unit step function, which has a value 1 for t greater than or equal to a and 0 for t less than a. Laplace of the displaced unit step function, that is u of t minus a, is equal to e raised to power minus as upon s, and inverse Laplace transform of e raised to power minus as upon s is u of t minus a. Further, we can prove that the Laplace of u of t minus a is equal to integration 0 to infinity e raised to power minus st into u of t minus a dt, which has a value 0 for the interval 0 to a and it has a value 1 for the interval a to infinity. So just break the interval 0 to infinity in two intervals, one from 0 to a and another from a to infinity, and integrate the function e raised to power minus st and substitute the upper and lower limit. We'll get the Laplace transform of u of t minus a is equal to e raised to power minus as upon s. Now there are few important cases that we have to discuss with this unit step function. The first case is if the function f of t is multiplied by unit step function u of t, then the product of f of t into u of t is given by, it has a value 0, that is the value of f of t into u of t is 0 if t is less than 0. As u of t is 0 for t less than 0, the value of f of t into u of t is 0 for t less than 0, and it has a value f of t for t greater than 0 because u of t has a value 1 for t greater than 0, and f of t into u of t represents the part of f of t to the right of t equal to 0. With this graph we can see that this is a function f of t, and when this f of t is multiplied with the unit step function u of t, the left portion, or we can say that the graph which is left to t equal to 0, it is being cut off. So this part of the graph which is left to t equal to 0 is being cut off. And the Laplace transform of f of t into u of t is equal to f of s, because u of t has a value 1 for t greater than 0. So its Laplace transform is equal to f of s. And the inverse Laplace of f of s in terms of unit step function is f of t into u of t. Case number 2. If the displaced function f of t minus a is multiplied by displaced unit step function u of t minus b, then the product of f of t minus a into u of t minus b takes the two values. The one value is 0, which is for t less than b, and it has a value f of t minus a for t greater than b. This is just because of u of t minus b is 0 for t less than b, and it has a value 1 for t greater than or equal to b. That's why f of t minus a into u of t minus b has two values, 0 and f of t minus a. And graphically, the first graph shows that the original function f of t and the displaced function f of t minus a. And if the displaced function f of t minus a is multiplied with the displaced unit step function u of t minus b, the part of the graph f of t minus a which is left to t equal to b is being cut off. So the part of the graph which is left to t equal to b is being cut off. Now we had a second shifting property which is based on the product of f of t minus a into u of t minus a. So if the product of f of t minus a into u of t minus a is denoted by g of t, which is equal to 0 for t less than a, and it has a value f of t minus a for t greater than a, then we have to check that or show that the Laplace transform of g of t or the Laplace transform of f of t minus a into u of t minus a is equal to e raised to power minus as into f of s. Okay. So we'll start with the actual definition of the Laplace transform, which is equal to integration 0 to infinity e raised to power minus st. Here we have to find out the Laplace of f of t minus a into u of t minus a. So multiply e raised to power minus st with the function, that is f of t minus a into u of t minus a into dt. Then u of t minus a has a value, this function actually f of t minus a into u of t minus a has two values. For the interval 0 to a, it has a value 0, and for a to infinity the function has the value f of t minus a. So substitute it in the integration and put t minus a is equal to x, so that dx is equal to dt, and as t tends to a, x tends to 0, and when t tends to infinity, x tends to infinity. And because of this integration changes to integration 0 to infinity e raised to power t becomes x plus a, so e raised to power minus s into x plus a f of x dx. As e raised to power minus as is constant with respect to x, so we shift it to the outside of integration. So it is e raised to power minus as integration 0 to infinity e raised to power minus sx f of x dx, and according to definition this is f of s. So Laplace of f of t minus a into u of t minus a is e raised to power minus as into f of s, which is also called as the second shifting property. And if we take the Laplace inverse of e raised to power minus as into f of s, which is equal to f of t minus a into u of t minus a. Now third case is very important for us. If the function f of t is multiplied by displaced unit step function u of t minus a, then the product of f of t into u of t minus a is equal to 0 for t less than a, and it is equal to f of t for t greater than or equal to a. And the Laplace of f of t into u of t minus a is equal to e raised to power minus as into Laplace of f of t plus a. So while finding the Laplace of f of t into u of t minus a, we have to write down the Laplace of u of t minus a as e raised to power minus as, and we don't take the Laplace of f of t directly. We need to shift the function by plus a. So take the Laplace of f of t plus a. Okay. Now next is how to express the given function in terms of unit step function. So if the particular function is given in terms of interval, so f of t has a value f1t for the interval 0 to a1. It has a value f2t for the interval a1 to a2, then f3t for the interval a2 to a3, and likewise. Then f of t in terms of unit step function is given by f of t is equal to f1t into u of t minus 0, that is t minus lower bound, minus u of t minus a1, that is upper bound, plus f2t into u of t minus lower bound for that particular interval t minus a1 minus u of t minus a2, plus f3t in bracket u of t minus a2 minus u of t minus a3, and so on. In the next step, f of t is equal to, we'll take the terms which contain u of t only. So we have only one term, that is f1t into u of t, and further we'll take the terms which contain u of t minus a1 in one bracket. So u of t minus a1 is common, and f2t minus f1t, plus u of t minus a2 common, in bracket we have f3t minus f2t, and similarly plus u of t minus a3 common, f4t minus f3t, and if we have further more intervals, we need to carry on like this. Now remember, Laplace of f of t into u of t is equal to f of s, and Laplace inverse of f of s in terms of unit step function is f of t into u of t. Laplace transform of f of t minus a into u of t minus a is e raised to power minus as into f of s, and Laplace inverse of e raised to power minus as into f of s is equal to f of t minus a into u of t minus a. And the most important, that is Laplace of f of t into u of t minus a is equal to e raised to power minus as into Laplace of f of t plus a. Whenever you find e raised to power minus as, that means it is a Laplace of unit step function. Now we will check the Laplace transform of the sum function which are expressed in terms of unit step function. For that we need to recall that Laplace of f of t into u of t minus a is equal to e raised to power minus as into Laplace of f of t plus a. So just take the first example. Here we have to find out the Laplace transform of t square into u of t minus 2. So the Laplace of t square into u of t minus 2. So here u of t minus 2 is the displaced unit step function. So its Laplace is e raised to power minus 2s into Laplace of, we need to shift this t by plus 2. So t plus 2 whole square, which is equal to e raised to power minus 2s. Laplace of t plus 2 whole square means t square plus 4t plus 4, which is equal to e raised to power minus 2s. Laplace of t square is 2 upon s cube. Laplace of 4t is 4 upon s square, and Laplace of 4 is 4 by s. Second is Laplace of e raised to power minus 2t into u of t minus 1. Here u of t minus 1 is the displaced function or displaced unit step function, and e raised to power minus 2t is what the shifting property. So for this, Laplace is e raised to power minus s upon s. The Laplace of this displaced unit step function is e raised to power minus s upon s, and we need to shift this s by s plus 2. So final answer for this function is e raised to power minus of s plus 2 upon s plus 2. Next, function is sin t, and it is multiplied by displaced unit step function u of t minus pi. So for u of t minus pi, the Laplace of that is e raised to power minus pi s, but the Laplace of sin t is, in that sin t we need to shift by t plus pi. So e raised to power minus pi s into Laplace of minus sin t, because sin of pi plus t is minus sin t. Pi plus theta is, sin of pi plus theta is minus sin theta. So minus sin t, and the Laplace of minus sin t is minus of e raised to power minus pi s upon s square plus 1, as Laplace of sin t is 1 upon s square plus 1. Now we'll check the inverse Laplace transform for the sum function. For that we need to recall that Laplace inverse of e raised to power minus as into f of s is u of f of t minus a into u of t minus a. So here we have the first example, Laplace inverse of e raised to power minus pi s upon s square plus 1. So for e raised to power minus pi s, we have the displaced unit step function as u of t minus pi, and here f of s is 1 upon s square plus 1. So Laplace inverse of 1 upon s square plus 1 is sin t, and we need to shift the function by t minus pi, because here a is pi. So final answer is sin of t minus pi into u of t minus pi. Here a is pi. Second example is Laplace. We have to find out Laplace inverse of s into e raised to power minus 2s upon s square minus 1. So here f of s is s upon s square minus 1, and Laplace inverse of f of s is, that is Laplace inverse of s upon s square minus 1 is cos ht, and the displaced unit step function is, here Laplace of the displaced unit step function is e raised to power minus ds. So Laplace inverse of e raised to power minus 2s is u of t minus 2, and original function is cos ht. So write it f of t as f of t minus a. So here it is cos t minus 2. All previous examples are the counter examples. Now with this particular problem, we are going to express this f of t in terms of unit step function, and in the next part we will find out the Laplace transform of f of t. So first we will express f of t in terms of unit step function. So for that, f of t is equal to t square into u of t minus 0 minus u of t minus 2. That is the value of the function in the first interval, that is t square into u of t minus lower bound minus u of t minus upper bound. So u of t minus 0 minus u of t minus 2. So next value of the function f of t is 4t, that is for the interval t greater than 2. So here it is 4t into u of t minus 2. Now rewrite it as t square into u of t plus 4t minus t square and take out u of t minus 2 common. So this is what equation number 1, and we have completed the solution partially because we have expressed f of t in terms of unit step function. Now we'll take the Laplace transform of equation 1 on both sides, taking Laplace transform of equation 1 on both sides. So here we have Laplace of f of t is equal to Laplace of t square into u of t plus Laplace of 4t minus t square into u of t minus 2. So this is something like f of t into u of t, and this is like f of t into u of t minus a. So you just need to recall. Here I am writing recall. Laplace of f of t into u of t minus a, which is e raised to power minus as into Laplace of f of t plus a. So we'll use this with the second term, and this is what Laplace of t square, just because Laplace of f of t into u of t is Laplace of t square, and for this we have e raised to power minus 2s into Laplace of 4 times t plus 2 minus t plus 2 whole square. We need to shift t to t plus 2. So here we have Laplace of t square plus e raised to power minus 2s Laplace of 4t plus 8 minus of t plus 2 whole square means minus t square minus 4t minus 4. So plus 4t minus 4t get cancelled, and Laplace of t square is 2 upon s cube plus e raised to power minus 2s Laplace of 8 minus 4, that is 4. So it is 8 minus 4 is 4, and Laplace of 4 is 4 upon s, and Laplace of minus t square is minus 2 upon s cube. The next example that we have is, we have to express the function f of t which has a value sin t for the interval 0 to pi, sin 2t for the interval pi to 2 pi, and sin 3t for t greater than equal to 2 pi. And we will also find its Laplace transform. So first step, that we have to express it in terms of unit step function. So we will write the solution. F of t is equal to sin t into u of t minus 0, that is u of t minus pi minus u of t minus pi, plus sin 2t u of t minus pi minus u of t minus 2 pi, plus sin 3t u of t minus 2 pi. Now collect the terms of u of t minus pi, and u of t minus 2 pi. So sin t into u of t, then plus the term containing u of t minus pi is sin 2t minus sin t u of t minus pi common plus sin 3t minus sin 2t u of t minus 2 pi common. Give it as equation number 1. So here we have finished with the expressing f of t in terms of unit step function. So we have expressed f of t in terms of unit step function. Now we have to take the Laplace transform on both sides of equation 1. So here we have the Laplace of f of t is equal to Laplace of sin t into u of t plus Laplace of sin 2t minus sin t into u of t minus pi plus Laplace of sin 3t minus sin 2t into u of t minus 2 pi. So which is equal to, here sin t is like f of t and this is u of t. So we have to apply the result of Laplace of f of t into u of t. But with this case, sin 2t minus sin t is acting as f of t, which is multiplied with displaced unit step function. So for this we need to recall Laplace of f of t into u of t minus a is e raised to power minus as into Laplace of f of t plus a. So we will apply the same result here. So Laplace of f of t is Laplace of sin t into u of t is just Laplace of sin t plus e raised to power minus pi s Laplace of sin 2 times t plus pi minus sin t plus pi plus e raised to power minus 2 pi s Laplace of sin 3 t plus 2 pi minus sin 2 times t plus 2 pi. So Laplace of sin t as it is plus e raised to power minus pi s. This is what Laplace of sin 2t plus 2 pi, and 2 pi plus 2t is sin 2t. Sin pi plus theta is minus sin theta, so it becomes sin t plus e raised to power minus 2 pi s Laplace of sin 3t plus 6 pi. So sin 6 pi n pi plus theta is sin theta, so it is sin 3t, and again sin 2t plus 4 pi is minus sin 2t. So minus sign will remain as it is. So n pi plus theta, when n is even, it is sin theta, and when n is odd, it is minus sin theta. So now just need to take the Laplace of this. So Laplace of sin t is 1 upon s square plus 1 plus e raised to power minus pi s in bracket. Laplace of sin 2t is 2 upon s square plus 4 plus Laplace of sin t is 1 upon s square plus 1 plus e raised to power minus 2 pi s common. Laplace of sin 3t is 3 upon s square plus 9, and Laplace of sin 2t is 2 upon s square plus 4. So this is what the Laplace of the given function f of t. Similarly, you can solve the example. Here you have to express f of t, which is given in the interval 0 to pi, and for t greater than pi, you need to express this function in terms of unit step function and find its Laplace transform.